Hello and welcome to ControllersTech. In the previous video, we looked at event flags, how they allow tasks to wait for one or multiple events before taking action, and how interrupts can use them to signal tasks, without performing any heavy work inside the interrupt service routine. In this video, we are going to look at something a little different, software timers. Let me start by explaining what a software timer actually is. In a typical embedded system, if you want to do something repeatedly, for example, blink an LED every 500 milliseconds, you would normally use a hardware timer. But hardware timers are a limited resource. Your microcontroller only has a few of them, and they are often already in use for other purposes, such as PWM generation or input capture. A software timer solves this problem by relying on just one hardware timer underneath, managed by FreeRTOS, and allowing you to create as many virtual timers on top of it as you need. Each software timer can call a function, known as a callback function, when its time period expires. Now, there are two types of software timers, a periodic timer and a one-shot timer. A periodic timer keeps repeating. Once the time period expires, the callback function runs, the timer resets, and it starts counting again. This cycle continues indefinitely, or until you explicitly stop it. A one-shot timer, on the other hand, fires only once. After the period expires and the callback runs, the timer stops on its own. If you want it to run again, you have to restart it manually. Now, there is one important thing to understand about how these timers actually work inside FreeRTOS. FreeRTOS does not run the timer callbacks inside your task or inside an interrupt. Instead, it uses a dedicated background task called the timer daemon task, also referred to as the timer service task. Whenever a timer expires, FreeRTOS sends a message to this daemon task through a queue, and the daemon task is then responsible for calling the appropriate callback function. This has a couple of important implications. First, your callback function should be short and should never block. If you place a long delay inside a timer callback, it will hold up the daemon task, and delay all other timer callbacks that are waiting in the queue. Second, the priority of the timer daemon task matters. If its priority is set lower than your other tasks, the callbacks may not fire on time. We will keep these points in mind as we go through the example. In this video, we will cover three things. First, we will create a periodic timer that prints the logs at a fixed interval. Then, we will create a one-shot timer that triggers once after a set delay. And finally, we will see how to start, stop, and reset a software timer from within a task. Let's open CubeMX and set up the project. We are going to create a new project for this video. Go to middleware and enable FreeRTOS with CMSIS version 2. Leave the basic configuration parameters at their default values, as we have already covered those in earlier videos. Now go to the Tasks and Queues section. A default task is already created here with normal priority, and a stack size of 128 words. We will be using this default task in our project, so leave it as it is. Next, go to the Timers and Semaphores tab. Here you will find a dedicated section for software timers where you can add new ones. We will create both of our timers from this section. Click Add to create the first timer. In the Type field, you will see two options, periodic and one-shot. We will create the periodic timer first, so select periodic. Set the timer name to periodic timer, and the callback function name to PT callback. Leave the remaining settings at their defaults, and make sure the allocation is set to dynamic, so the timer allocates its memory from the FreeRTOS heap. Click Add again to create the second timer. This time, select one shot as the type. Name it one-shot timer and set its callback function to OST callback. Leave everything else at the default values. Both timers are now created, and we already have our default task in place. If you go to the FreeRTOS heap usage section, you can see that around 2 kilobytes of heap memory is still available, so this configuration is perfectly fine to work with. We will also be printing logs to the serial console, so we need to enable a UART peripheral. On the Nucleo L496 board, the ST-Link virtual COM port is connected to low-power UART1, so enable this peripheral in asynchronous mode. Configure it with a baud rate of 115200, 8-bit word length, no parity, and 1 stop bit. By default, CubeMX assigns pins PC0 and PC1 to LP UART1. However, if you check the schematic of the L496 board, you will notice that the ST-Link RX and TX lines are actually connected to pins PG7 and PG8. So we need to reassign LP UART1 to use PG7 and PG8 instead. Next, I am also going to connect a button to the pin PA3, so configure this pin as a GPIO input. There is also an onboard blue LED connected to pin PB7, set this pin as a GPIO output. You can see in the board schematic, the blue LED is connected to the pin PB7. Now go to System Core and open the GPIO configuration. Set the button pin to pull-up mode. This means the pin will read high by default, and when the button is pressed, it will be pulled low. That transition from high to low is what we will use to detect a button press. Since we are using FreeRTOS, we also need to change the HAL timebase source away from SysTick. This is because FreeRTOS uses SysTick internally for its own tick management, so the HAL layer needs a separate, dedicated timebase to avoid any conflict. Here, we are selecting Timer 6, which is a basic general-purpose timer with minimal features. You can choose any other available timer as well, the important thing is just that it is separate from SysTick. Next, go to FreeRTOS Advanced Settings, and make sure the new lib reentrant option is enabled. This ensures that standard C library functions like printf work correctly in a multi-threaded FreeRTOS environment, where multiple tasks could potentially call such functions at the same time. Now go to Project Manager, set the toolchain to STM32 Cube IDE, give the project a name, and click Generate Code. Once the code has been generated, we will import the project into Cube IDE. The project has now been imported, and we can see the main file of our new project. If you look at the main function, you can see that CubeMX has already generated the initialization code for both timers, the periodic timer and the one-shot timer, along with the default task that we will be working with. Now scroll down to the task function. Keep in mind that while both timers have been created, they do not start automatically. We need to start them manually from within our code. When execution enters the default task, the first thing we will do is start the periodic timer. To do this, we call the function OSTimerStart. Since this line runs only once at the beginning of the task, before the infinite loop, it is the right place to start the periodic timer, as it is designed to run continuously and repeat on its own. This function takes two parameters. The first is the timer handle, which in our case is the periodic timer handle. The second is the time interval in milliseconds, which determines how often the callback function is called. We are setting this to 1000 milliseconds, meaning the periodic timer callback will be triggered once every second. Inside this callback, you can perform various lightweight operations, such as setting event flags or printing a short message to the console. In our case, we are simply printing a log message to indicate that the periodic timer callback has been called. As mentioned earlier, always keep timer callbacks short and non-blocking. After starting the periodic timer, the task enters its infinite loop. Inside this loop, we continuously check for a button press. If pin PA3 reads low, it means the button has been pressed and the pin has been pulled to ground. When that happens, we turn the LED on by setting pin PB7 high, and then start the one-shot timer using OS timer start, this time with a delay of 5000 milliseconds. This means the one-shot timer will expire 5 seconds after the button is pressed. Once it expires, the OST callback function is called. Inside this callback, we turn the LED off by resetting pin PB7, and print a log message to confirm that the one-shot timer has fired and the callback has executed. Since we are using printf, make sure to include the standard I/O header file at the top of your source file. We will also use our custom retarget function to redirect printf output through LPWAT1, so that the log messages appear correctly on the serial console. That is all the code we need for this example. Let's go ahead and build the project. The build completes with no errors, so we are ready to flash the firmware to the board. Open the serial console to view the logs. You can see that the periodic timer callback is printing a message every 1 second. This confirms that the periodic timer is running correctly, and its callback is triggering at the expected interval. Now let's press the button. As you can see, the LED on the STM32 Nucleo board has turned on, indicating that the button press was detected, and the one-shot timer has started. We will now wait for 5 seconds. The LED has turned off, and the corresponding log message has appeared on the console. This confirms the expected behavior. When the button was pressed, the one-shot timer started counting. After 5 seconds, the timer expired, the OST callback function was called, the LED was turned off, and the log message was printed. Now let's explore something interesting. What happens if we keep pressing the button before the 5 seconds are up? Every time the button is pressed, the timer start function is called again for the one-shot timer. This does not create a new timer or stack multiple timers on top of each other, it simply resets the existing one, pushing the expiry point forward by another 5 seconds from the moment of the latest press. As long as we keep pressing the button within the 5-second window, the timer keeps getting reset, it never expires, and the callback is never triggered. This behavior makes the one-shot timer particularly useful for scenarios like debounce logic, or inactivity detection. It also works well as a lightweight alternative to a watchdog timer, and since it integrates naturally with FreeRTOS, it fits cleanly into a multitasking application without any extra complexity. Now, just like starting a timer, we can also stop a running timer and check whether it is currently active. For example, when the button is pressed, we can check if the periodic timer is currently running by calling the function OSTimerIsRunning. This function returns 1, if the timer is active and currently counting. If it is running, we then call OSTimerStop to stop it immediately. To restart it at a later point, we call OSTimerStart again. We do this inside the one-shot timer callback. Once the 5 seconds have elapsed and the callback fires, we check if the periodic timer is stopped, which is indicated by OSTimerIsRunning returning 0. If it is stopped, we restart it with a 1-second interval, and it resumes running as normal. Let's test this behavior. You can see the periodic timer is running correctly, and printing a log message every second. Now when we press the button, the periodic timer logs have stopped appearing on the console, confirming that the timer has been successfully stopped. After 5 seconds, the one-shot timer expires, its callback runs, and the periodic timer is restarted. The log messages begin appearing on the console again, exactly as expected. So I hope you now have a clear understanding of how software timers work in FreeRTOS. We saw how to create both, a periodic timer and a one-shot timer in CubeMX, how to start and stop them from within a task, how to check whether a timer is currently running, and how the one-shot timer can be reset by simply calling OSTimerStart again before it expires. You can download the project from the article linked in the description of this video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.